The chemistry behind God's drug, morphine. Today we'll be looking at all 5 units of the SCH4U course and how they connect to morphine. About morphine. God's drug, better known as morphine, is an opiate, a highly addictive, naturally occurring drug derived from the resin in the opium poppy plant. It acts on the nervous system to remove pain, although it isn't as dangerous as its counterparts, such as fentanyl, heroin, or oxycodone. It does outdate them as the first isolated opium in 1805 by William Sturtner. But the use did not become widespread until nearly 50 years later, when the hypodermic needle and the syringe became commonplace. To this day, morphine remains the most widely used analgesic and the standard which opiates are compared to for post-operative pain relief. Now let's delve into the chemistry behind what makes morphine. Unit 1. Structure. Let's start with hybridization. Many carbon atoms are sp3 hybridized, meaning they form 4 sigma bonds with tetrahedral geometry around 109.5 degrees. The carbon atoms involved in the aromatic benzene ring are sp2 hybridized. These atoms form trigonal planar structures with bond angles near 120 degrees. Hybridization directly affects morphine's shape, rigidity, and biological activity because receptor binding depends heavily on molecular geometry. Let's move over to quantum numbers and electron organization. The atoms inside morphine contain electrons arranged according to quantum mechanics. An example of this is oxygen. 1s2, 2s2, 2p4. Its valence electrons occupy p orbitals, allowing oxygen to form polar covalent bonds and hydrogen bonds. The nitrogen in morphine contains a lone pair of electrons, which allows it to interact with opioid receptors in the brain. VSEPR theory and molecular shape. Using VSEPR theory, we can predict the molecular geometry of morphine. The oxygen atoms have bent molecular geometry because lone pairs repel bonding electrons. The tetrahedral carbon arrangements create a 3-dimensional structure that perfectly fits opioid receptors in the nervous system. Now let's take a look at intermolecular forces, including H-bonding, dipole-dipole, and London dispersion force. Morphine exemplifies several intermolecular forces. The hydroxyl groups allow hydrogen bonding, making morphine somewhat soluble in water. Morphine also experiences dipole-dipole forces because of polar containing groups and London dispersion forces from its hydrocarbon regions. These intermolecular forces affect boiling point, solubility, and how morphine travels through the bloodstream. Let's look at organic chemistry. Functional groups. Morphine encompasses several important functional groups. It contains an aromatic ring, alcohol groups, an ether linkage, and a tertiary amine. Each functional group contributes to morphine's chemical behavior and biological effects. For example, the amine group allows morphine to bind to receptors, while hydroxyl groups increase polarity. Taking a look at organic reactions, we can see that morphine can undergo important organic reactions, such as acetylation, where morphine reacts with acetic anhydride to form heroin, also known as diacetylmorphine. This reaction replaces hydroxyl hydrogens with acetyl groups, increasing lipid solubility and allowing heroin to cross the blood-brain barrier even quicker than morphine. Isomerism. Morphine demonstrates stereoisomerism because it contains multiple chiral carbons. This means atoms can be arranged differently in 3-dimensional space, even with the same molecular formula. Only one specific stereoisomer of morphine strongly binds opioid receptors. Small changes in spatial arrangement can dramatically alter biological effects. Intermolecular forces and properties. Morphine's intermolecular forces strongly affect its properties. Hydrogen bonding increases water solubility, but slows down movement across lipid membranes. Heroin, which forms fewer hydrogen bonds, enters the brain faster, making it more potent and addictive. Energy changes and rates of reaction. Endothermic versus exothermic reactions. When morphine binds to opioid receptors, energy changes occur. Some biochemical reactions involved in metabolism absorb energy and are endothermic. Others release energy and are exothermic, especially reactions involved in cellular respiration during drug metabolism. Let's look at collision theory. When morphine enters the bloodstream, its molecules move randomly and collide with receptor sites in the brain and nervous system. Although not every collision leads to binding, as the morphine needs to collide to the receptor in the correct orientation and with enough kinetic energy. Morphine contains hydroxyl groups and a nitrogen containing amine group that help it interact with receptor sites through intermolecular forces, such as hydrogen bonding and dipole-dipole interactions. The IMFs help add stability to the reaction and allow for a stronger bond between the morphine and the receptor, therefore increasing the likelihood of the collision sticking after colliding. Catalysts and reaction pathways. In the liver, enzymes act as a biological catalyst during morphine metabolism. Catalysts lower activation energy by providing an alternative reaction pathway. This allows morphine to break down more quickly without the catalyst itself being consumed. Factors affecting reaction rate. Several factors affect the rate of reaction involving morphine in the body. A major factor is temperature. As temperature increases, particles gain kinetic energy and move faster. According to collision theory, this leads to more frequent and more energetic collisions between molecules, increasing the chance that collisions overcome activation energy and successfully react. Furthermore, method of administration matters equally, as intravenous injection causes morphine to act much faster than oral consumption because it enters directly into the bloodstream instead of passing through the digestive system to be broken down. Enzyme concentration also affects how rapidly morphine is metabolized, as aforementioned about liver enzymes. The concentration of morphine itself can also increase the reaction rate because a greater number of particles lead to more molecular collisions. Equilibrium. Le Chatelier's principle. Morphine exists at equilibrium between ionized and non-ionized form. According to Le Chatelier's principle, changes in pH shift this equilibrium in acidic environments. More morphine becomes protonated and water-soluble. In more basic environments, more non-ionized morphine forms increasing membrane permeability. This equilibrium affects how morphine is absorbed and distributed throughout the body. Let's look at buffers and their function and pH and pOH calculations. The human body maintains a homeostatic balance near a pH of 7.4 in your blood using buffer systems. Buffers resist sudden change in pH, helping maintain stable conditions for biochemical reactions. Since morphine behaves as a weak base, blood pH affects whether it exists in ionized or neutral form. Chemists use pH calculations to determine hydrogen ion concentration and predict morphine's behavior inside the body. Let's take a look at the final unit in SCH4U, electrochemistry. Redox reactions. Morphine metabolism also involves redox reactions. Redox reactions involve electron transfer. Oxidation occurs when electrons are lost, while reduction occurs when electrons are gained. During metabolism, liver enzymes oxidize morphine into more weather-soluble metabolites that can be excreted through urine. These redox processes are essential for detoxification and drug removal. Electrochemical cells. Electrochemical cells are connected to morphine through redox reactions, used in medical analysis. When morphine undergoes an oxidation reaction and loses electrons, this reaction, if it were an electrochemical cell, would occur at the anode. This flow of electrons produces an electric current. Electrochemical techniques are used to detect and measure morphine concentrations in blood, urine, and pharmaceutical samples. Specialized sensors can oxidize morphine at an electrode surface and measure the resulting current. The magnitude of the current is proportional to the concentration of the morphine present. Finally, our conclusion. Morphine is much more than a painkiller. Its effects are controlled by hybridization, molecular geometry, intermolecular forces, stereochemistry, energy changes, equilibrium chemistry, and redox reactions. By studying morphine, we can connect nearly every facet of all the major concepts in the SCH4U course to a real-world natural molecule that shaped modern medicine, from atomic orbitals to biochemical reactions. Chemistry explains not only how morphine relieves pain, but also why it can become so addictive and how it interacts with the human body. Morphine demonstrates the powerful relationship between chemistry, biology, and human health. Thank you very much for watching.